Practically all modern naval ships of the destroyer class or larger are powered by steam. Steam made in the ship's own steam plant propels the ship, generates electricity, and powers auxiliary machinery. The boiler generates the steam, the turbines use it, the condenser system reduces the used steam to feed water, and the feed system returns the feed water to the boiler to be turned into steam again. In other words, the ship's steam plant is continuously turning water into steam, steam back into water, and water back into steam. This continuous process is called the steam cycle. In this film, we will study the steam-making phase of the steam cycle in order to learn how boilers work. Since the DE, or destroyer escort boiler, contains the physical features characteristic of all naval boilers, we will study the operation of this particular boiler. For simplification, we will use drawings that show only one burner in the boiler furnace, although most boilers have a number of burners. The furnace and the burners provide the heat needed to turn the water into steam. Fuel oil is sprayed into the furnace, mixed with air into a combustible mixture, and burned. The hot combustion gases heat the water in the bank of tubes called the generating tubes. Bubbles of steam form in the water in the generating tubes. The mixture of water and steam rises to a large cylindrical vessel, the steam drum. Here the steam, called saturated steam, is separated from the water and sent to another bank of tubes, called the superheater, located within the bank of generating tubes. In the superheater, the steam is further heated and becomes superheated steam before going to the ship's turbines. The used steam returns as feed water and is preheated to some extent in a bank of tubes called the economizer before going to the steam drum. Meanwhile, in large tubes called downcomers, water is descending from the steam drum to a cylindrical vessel connected to the generating tubes, the water drum, and back into the generating tubes to be heated again. The downcomers are usually outside the inner boiler casing. There is another circuit of generating and downcomer tubes in the furnace sidewall in the DE boiler. A large tube called a header connects the tubes. Since the steam generated in this sidewall circuit carries off some of the furnace heat, these tubes help cool the furnace sidewall. We can thus see that a boiler consists of a furnace, generating tubes, superheater, and economizer, and that there are four principal phases in the process of turning feed water into superheated steam: combustion, feed water preheating in the economizer, steam generation, and steam superheating. Let's look at each of these phases in more detail. Combustion is the name given to the chemical reaction of the combustible particles of the fuel with oxygen in the air. The burner, seen here in a cutaway, provides a combustible mixture by atomizing the fuel oil. That is, by breaking it up into tiny particles and mixing the atomized particles with air. During complete combustion, the carbon in the fuel oil combines with oxygen in the air to form carbon dioxide. During incomplete combustion, a certain amount of the carbon becomes carbon monoxide. A pound of carbon burned to carbon monoxide gives approximately 4,400 BTUs of heat. A pound of carbon burned to carbon dioxide gives approximately 14,600 units of heat. Obtaining complete combustion is largely a matter of correct control of the amount of air that is mixed with the fuel oil. For any given amount of fuel, there is a theoretical weight of oxygen required to burn it completely, and therefore an exact amount of air. Since theoretical conditions cannot be met in actual boiler operation, In practice, more air must be supplied to the furnace to burn the fuel oil completely than in theory. This quantity of air above the theoretical requirement is called excess air. Too much excess air results in incomplete combustion, and in extreme cases, the unburned fuel leaves the stack as a fog or vapor called white smoke. Not enough excess air also results in incomplete combustion. In this case, all the carbon in the fuel oil is not burned, and this results in unburned carbon or soot. The soot is deposited on the boiler tube. This deposit reduces the degree of heat transfer to the tubes and the water and further wastes fuel. The soot may also cause the ship to give off black smoke. With the correct amount of excess air, combustion is complete. Flue gases have the appearance of a light brown haze and contain little or no carbon monoxide. To increase the rate of steam generation in a boiler, you must increase combustion by increasing both the amount of air and the amount of fuel going to the burner. However, the amount of air or the amount of fuel the equipment can supply has its limits. Thus, the rate of combustion, and therefore the rate of steam generation of a boiler, can be increased only to a certain point. That point is the end point of combustion, and is one of the measures of a boiler's capacity. After the combustion gases have passed through the bank of generating tubes, the economizer uses the heat still remaining in the gases to raise the temperature of the water returning from the feedwater system before it enters the steam drum. Thus, the heat and therefore fuel required to turn the water into steam in the generating tubes is reduced. About 1% of fuel is saved for each 10-degree rise in temperature in the water in the economizer. Some boilers also use an air heater. The air heater saves fuel by using the heat remaining in the combustion gases to heat the air going to the burners. When a boiler is operating, there is continuous circulation of the ascending mixture of steam bubbles and water in the generating tubes and the descending water in the downcomers. The steam-water mixture rises in the generating tubes because, due to the steam bubbles, the mixture is lighter and less dense than the water descending in the downcomers. This effect is called natural circulation, and boilers with this type of circulation are called natural circulation boilers. Most Navy boilers are of this type. At all rates of steam generation of a boiler, the level of water in the boiler must approximate the designed water level. As the rate of steam generation increases due to increased combustion, more of the water in the boiler becomes steam and goes to the superheater. More water must enter the boiler and circulate through the downcomers to hold the water level in the boiler. However, there is a limit to the quantity of water that can pass through the downcomers. Beyond this limit, some of the generating tubes will overheat and burn out. This limit is called the end point of circulation and is another measure of a boiler's capacity. The hotter steam is, the better it does its work in the ship's main propulsion turbines. In the steam drum, the saturated steam is in contact with the boiler water. As long as steam is in contact with water, any increase in the temperature of the steam can only be obtained by an increase in pressure. Thus, it is not practical to bring steam to the maximum desired temperature in the steam drum because of the tremendous pressure that would be encountered. However, if the saturated steam is taken out of contact with the boiler water by being sent to a separate bank of tubes, the superheater, the temperature of the steam can be raised without an increase in pressure. The result is superheated steam. Steam that has approximately the same pressure as the saturated steam, but a higher temperature. Note that the steam used for auxiliary machinery is drawn directly from the steam drum, since such steam does not have to be superheated. The high temperatures in the superheater tubes make the problem of scale on tube walls very important. Even though the steam flowing through the superheater tubes is very hot, the steam in effect cools the tubes because of the heat that the steam absorbs from the tube walls and carries off. However, saturated steam always contains some moisture as it enters the superheater. Moisture brings with it solid matter that is deposited as scale on superheater tube walls. Scale reduces heat absorption by the steam, and tube temperatures rise. If the scale gets thick enough, so little heat is absorbed from the tube walls that the tubes overheat and burn out. Thus, the amount of moisture that is carried over with the saturated steam entering the superheater must be kept at a minimum. The amount of moisture in the saturated steam increases with the rate of steam generation. This is because the steam bubbles break through the water more violently. In the DE boiler, a baffle reduces the violence of this action, thus reducing the amount of moisture in the steam. The steam then passes through a series of small holes in the dry pipe, and more moisture is removed before the steam goes to the superheater. However, in any type boiler, there is a point where the rate of steam generation produces more moisture than can be effectively handled. Any further increase in steam generation would result in a degree of moisture carryover that would endanger the superheater tubes because of scale deposits. This is called the end point of moisture carryover, and is still another measure of a boiler's capacity. Now let's review briefly how a boiler works. Hot combustion gases from the furnace pass through the generating tube banks, superheater, and the economizer. Feed water flows through the economizer, where it is preheated, to the steam drum, where it mixes with the water already in the boiler. The water leaves the steam drum, goes through the downcomers, to the water drum and header, then into the generating tubes. The steam-water mixture rises to the steam drum, where the steam is separated from the water. The separated, saturated steam goes to the superheater, becomes superheated steam, and goes to the turbine. Thus, there are 4 principal phases in the continuous process of turning feed water into superheated steam: combustion, feed water preheating in the economizer, steam generation, and steam superheating. In order to obtain complete combustion and efficient boiler operation, the correct amount of excess air is essential. Black smoke means too little air and danger of soot deposits on the tubes. White smoke means too much air. When flue gases have the appearance of a light brown haze, the amount of air is correct, and combustion is complete. When the supply of air or fuel oil reaches its limit, the end point of combustion is reached. The economizer is still remaining in the hot combustion gases to heat the water before it enters the steam drum. It thus reduces the heat required to turn the water into steam in the generating tube. In natural circulation boilers, there is constant circulation of the descending water in the downcomers and the ascending, less dense steam-water mixture in the generating tubes. Comer capacity is reached. In the superheater, saturated steam becomes superheated steam. This steam has a higher temperature, but approximately the same pressure as the saturated steam entering the superheater from the steam drum. The end point of moisture carryover is reached when the total capacity of the baffles and other moisture-removing devices cannot carry over below tolerable limits.